This one is C6H13ON. It has one double bond equivalent. The groups that I see here, I have a 3H and a 6H. Now we've got to decide whether this 6H is going to be 2 CH3s or 3 CH2s. And what we can do is we can usually say this, and that is if there's one peak or two peaks or three peaks for the 6H, that generally indicates we're looking at 2 CH3s, and when there's four peaks we're generally looking at 3 CH2s. All of this is demanded by symmetry, and if you'd like you can stop the video and you can read about that here. So we've got 3 CH3 groups, and we also have a CH and a CH2 group. So what have we got left over? We've got a C, an H, an O, an N, and a double bond equivalent. Now since there's no C double bond N possible here out of these pieces, and the C double bond O is more likely than a C double bond N anyway, and I'm going to say that we have a C double bond O, which only leaves us then with an N and an H, so that would be an NH group over here, and that would match the 1H broad that we have here. So you had to determine whether it was an NH or an OH, and since we have a C double bond O here, then it's most likely to be an NH and not an OH. So those are the pieces. Now we can put them together. The CH3 will go over here, and then we've got to figure out what's going on with this CH. You can see here the CH has a total of 9 peaks, and that would indicate then that it has 8 adjacent hydrogens. So I know that the CH is most likely going to be in this kind of environment. That is 2 CH3 groups and a CH2 for a total of 8 adjacent hydrogens to account for these 9 peaks. Now I've also got to account for the C double bond O and the NH3, the CH3. I know that the CH3 cannot connect down here, because if it did, the CH3 would end up having multiple peaks. It would have 3 peaks because it would be adjacent to a CH2. Now I know that this CH3 must be this CH3 here, because these two CH3s must be the one under the 6H, because they're equivalent and they're adjacent to one hydrogen. So this CH3 must be this one here, and it's going to be apart from the CH2. Now I've got to decide where the C double bond O and the NH are going to go. Now looking at the chemical shifts involved here, we can see that we have a CH that is going to be, we can have a CH3 here that's at about 2.4 ppm, and we can see that CH2 is at about, say 2.1 ppm. Now this is fairly subtle, but I would say that based upon what I see on the correlation chart, we can see that C double bond O, CH is connected to C double bond O's usually actually appear between 2 and 2.5 ppm, and CH is connected to nitrogens usually appear a bit higher than that, say 3 to 3.5 ppm or 2.5 to 3.5 ppm. But what I can say, just even based on this correlation chart, is that CH's connected to N's are usually going to be downfield from CH's connected to C double bond O's. So that's why I would say that this would be the correct arrangement, as opposed to this one, which would place the CH3 down here and the CH2 up here. So I would switch these around, and I would make that my final structure.